As we move into our final unit, Chapter 7, Section 1, we're going to focus on oblique triangles. Now, oblique triangles, any triangle that is not a right triangle is oblique. Right here, a triangle that is not a right triangle is what we call an oblique triangle. And the measures of the three sides and the three angles of a triangle can be found if I know at least one side and any two other measures. So I have to have three pieces of information to solve an oblique triangle. One of those pieces of information has to be a side length. Okay, we have congruency axioms for our oblique triangles. Congruent triangles mean that they are the same size, same shape. If I know either one of these sets of information, side, angle, or side, side, then I can show that I have two triangles that are going to be congruent, same size and shape, to each other. Now, if I'm going to solve a triangle, that means I'm finding all the pieces of information about the triangle. The triangle has three sides, three angles. If I know three pieces and I want to solve the triangle, I'm finding the other three. Now, these are the four cases that can help me solve my triangles. The first case is when I know one side and two angles. And we can call that side angle, or angle, side, angle. Now, the order in which we list these letters is important. This is not the same thing. For this one, I have a side that is not between the two angles I know. For this one, I know the side that is between two angles. So, for example, if I know side, angle, then I might know this side and these two angles. So that would be side, angle. If I know angle, side, angle, that means I know the angle, the side between them, and then the other angle on the other side. So angle, side, angle, the side is between the two angles, physically on the triangle. Side, angle, the side that I know is not between the two angles that I know. Okay, so that order matters in how I list this, but both of these are the first case. If I know one side and two angles, it doesn't matter where that side is. Okay, for case 2, now this is what we call our ambiguous case, and we'll talk about why this one is ambiguous. Ambiguous means it's not always clear. The ambiguous case is when I know two sides and one angle, and that angle is not included between the two sides. So we're going to list that as side, angle. This case is ambiguous because it may lead to more than one triangle. Now, side, angle means that I know this side and this side, but I don't know the angle between. I know this angle, or maybe that one up there, but I don't know the angle between the two sides. This is my ambiguous case. It doesn't necessarily lead me to one shape, one size of my triangle. I could have two triangles that look differently. To remember which one is the ambiguous case, we read that sucker backwards. The ambiguous case is a pain. So side, angle. All right, case 3 is when I know two sides still and just one angle, but that one angle is included between the two sides that I know. So this one is side, angle, side. So when I look at my triangle, if I know this side and the angle between, that is side, angle, side. My fourth ambiguous case is when I know all three sides. Side, side. Not ambiguous. Oh, I said that wrong. Take that word totally back. The only ambiguous case is my side, angle, or angle, side. The solving triangles, I have 4 cases total. Case 2, this is ambiguous. These cases are not. Okay, if we know 3 angles of a triangle, we cannot find a unique side length. Angle assures us only similarity, not congruence. So you'll notice that I've got one side, two angles, two sides, one angle, a couple of different ways, or all three sides. But angle, angle, angle is not one of my triangle congruency axioms. It just assures similarity. Well, why is that? Well, let's say we have an equilateral triangle. If I have an equilateral triangle, that means all three sides are equal. It also means all three angles are equal. So if here I have a 60, 60, 60. So if I know angle, 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 I know that this is equiangular. All of my angles are 60 degrees. 60 degrees, 60 degrees, 60 degrees, because the sum is 180. Well, if I tell you I have an equiangular triangle, all three angles are 60 degrees, and I ask you to draw it for me, you might draw it this big, or you might draw it this big, where all three angles are the same, or you might draw it this big. All three of these have the same measures for the angles. Because I don't have a side length, I don't know how big I need to draw my triangle. So angle, angle, angle assures us that these triangles are going to be similar, they're going to be the same shape, but it doesn't assure that they're going to be congruent. We don't know if they're the same size. Okay, well, how do we solve? We've been, up until this section, we've been working with right triangle trig. We've been solving for right triangles. Oblique triangles, not right triangles, so we need some other tools to use to solve our oblique triangles. One of those tools that we're going to use is the law of sines. Now, the law of sines says that in any triangle ABC with sides ABC, where side A is opposite angle A, side B is opposite angle B, and side C is opposite angle C, I can say that these relations are proportional to each other. So if I set up these ratios, each of those ratios is going to be equal to every other ratio. Now the next page, I'm sorry, I got lost. I rearranged some things. According to the law of sines, the lengths of the sides in a triangle are proportional to the sines of the measures of the angle opposite them. And I can stack it the other way. So I can set it up so that I've got my side length in the numerator. I could also turn them upside down and arrange them so that the sine of the angle is in the numerator. This is law of sines because I'm using the sine of the angle over the side length. And this ratio is going to have the same value as this ratio, and it's going to have the same value as this ratio. So as long as I know one pair of information, I can solve for an unknown. All right, let's go back up here and derive the law of sines. We're going to work our way through to see where the law of sines comes from. To derive the law of sines, you're going to start with an oblique triangle, such as the acute triangle shown below on the left, or the obtuse triangle shown on the right. So you see we have triangle ABC. This is acute because all three angles are acute. We have triangle ABC. This is obtuse because angle A is obtuse here. Now, this discussion works with either type of triangle. If whichever type of triangle we have, we need a perpendicular because we want to reference a right angle because that's what we're comfortable with. So for the acute triangle, we drop the perpendicular from B straight down to the opposite side, and that perpendicular falls inside. For our obtuse triangle, if we drop the perpendicular down from B to the opposite perpendicular to the opposite side, this height falls outside the triangle. Let H be the height, the length of this perpendicular. So here is my height of my triangle. That means that C is the hypotenuse of the right triangle ADB. So I have created a right triangle. I've taken my acute or my obtuse triangle and I have created a right triangle where C is the hypotenuse because it is opposite that right angle. For this one, that's all we got, right? Oh no, we've got a little right triangle here, we've got a big right triangle there. C is the hypotenuse of ADB, A, however, is the hypotenuse of the triangle BDC. So we've set it up so that we've got two right triangles here, two right triangles here, and we see that we have a hypotenuse opposite that right angle. Well, sine, I know that sine is opposite over hypotenuse, right? So if I'm looking at angle A here, sine is opposite over hypotenuse, that's h over c. And if I take that and I solve for h, that means I'm going to multiply both sides by c. I get c times sine of A. For this other triangle, the big triangle here, or this bigger triangle here, if I'm looking at angle C, sine is opposite over hypotenuse, so now it's h over A, and right here, so sine of angle C is opposite over hypotenuse, h over A, no matter which of those triangles I'm looking at. So here, if I solve for h, I've got A times the sine of angle C. So what I've done is I've set it up so that I have two different values for h, and it's the same h, correct? Depending on whichever one of these situations I'm referencing, h is just h. I haven't redrawn it. So h is equal to c times the sine of angle A, and h is also equal to A times the sine of angle C. So we can set those two expressions equal to each other. A sine of C is equal to C, side C, times the sine of angle A. And if I divide both sides, so this is my, let's see here, this is my equation that I'm looking at. If I divide both sides by sine of C, I would have A, and then I've got sine. If I divide by sine of C, it's going to cancel over here, so I end up with sine of C over here. And then if I divide both sides by sine of A, I've got C up here. Divide out sine of A, that moves it over here. And there are two of the ratios in my law of sine. Now we could go back and we could rework it looking at other angles, and we could show that B over sine of B is also equal to A over sine of A. We're going to stop there with our derivation. Just remember a couple of things, that you're always looking at the ratio of the side and its angle that is opposite that side. Those ratios are equal to each other. So if I'm going to use law of sines to solve an oblique triangle, I need to know one pair of information. Which way do we stack it? Well, as you're getting used to this, some people really like to put the unknown in the numerator. It's not a bad thing. It's good to put the unknown in the numerator because it just makes it a little easier for us as we're solving to think about it. That helps me decide which way I'm going to stack my law of sines, if I'm going to put the side length on top or if I'm going to put sine of the angle on top. Okay, let's solve some triangles. Now we're going to solve triangle ABC. ABC is not a right triangle, it's oblique, and we're going to use law of sines. I have to start with a sketch, guys. You need a well-labeled sketch every single time. So we've got triangle ABC. Angle A is 28.8 degrees. Angle C is 102.6. Now notice I didn't draw it to scale. That's fine, doesn't matter. But I've got two angles, and then I know side C. Well, side C is opposite angle C, so this has to be side C, 25.3 inches. So I need three pieces of information. I need a third angle, and I need two side lengths. I need to find side A and side B, and I need to find angle B. Well, I'm going to start with the easiest thing first. I'm going to find angle B first. Because I know the sum of the angles in a triangle is 180. Then I take that 180 and I subtract the measures of the two angles that I know. And I figure out, okay, well, angle B, therefore, needs to be 48.6 degrees. Now I need to solve for side A and side B. Well, I'm going to use law of sines. I know a pair. I know angle C and side C. And I need to solve for side A and side B. All right, so this is what I know. I know that 25.3 over sine, we got to use law of sines, of 102.6 is going to be equal to, and it's going to be equal to A over the sine of angle A. And it's also going to be equal, same pair, this is what we know, 25.3 over sine of 102.6 degrees. That is also going to be equal to side B over angle B, sine of angle B, 48.6. All right. Now, solve using cross products. Well, this is a proportion. I solve it using cross products, so I multiply numerator on one side to the denominator on the other. So I get A sine of 102.6 degrees is equal to 25.3 times the sine of 28.8 degrees. And then to finish solving, I'm going to divide out this value of sine. And I will solve for A. Now, I'm going to, it looks like I've got 3 significant digits here. I've got 4 here, but I've got 3 here and here, so we're going to solve for 3 significant digits. We keep one decimal place, typically. In my calculator, mode matters because I'm using a trig function, so I need to make sure I'm using degrees, so I need to make sure I'm in degree mode, so I'm going to need to switch back to degree mode. And I'm going to work this out. So my numerator is 25.3 times the sine of 28.8. That's my numerator, and then I need to divide that by the sine of 102.6 degrees.